దా బంగారు కొండ బంగారు కొండ బంగారు కొండ దా 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 ఎక్కడ ఉన్నది పక్కన దా. వాళ్ళ తలుపు దగ్గరే కోపం వచ్చింది తలుపు దగ్గర దా ఇక దా అంటే ఇష్టం నాకు నానంటే ఇష్టం లేదు దా 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 కొడతాను, దా.
So I hope I'm audible. Can you please confirm if I'm audible?
Yes, sir.
Okay, fine. So let's start live session for week 9. So I am Anan Singhal, a PhD student from IIT Jodhpur, and I'll be assisting you solving the similar problem to week 9 assignments for the course Digital Electronic Circuits, which is taught by Professor Gautam Shah from IIT Kharagpur. So till now in the previous weeks, we have almost covered the each and every aspect of the combinational part of the circuit. And then from week 6, we started this sequential part, which is still going on, and it will end with the sequential part only. And in the week 6, not 6, but from week 7, we started the sequential circuit. And in week 7 and 8, we have already studied about different types of flip flops, different representation, different types of counters, also some of them which are almost all of them were synchronous counter. That is, they were having a single clock. And in this class or in this week's lecture, we'll be studying about some more counters such as up and down counters, some of the asynchronous counter. I'll let you know what is the difference between asynchronous and asynchronous counter. And then we'll see some of the counter designs with reset or preset circuits, and then some of the applications of the counters. So without further much waiting, let's start with the first question itself. So the first question states that a ripple counter with a positive asterisk. So you need to be quite aware of the triggering of the flip flop or the triggering of the flip flop or the clock of the circuit. So it is given that it is a positive edge triggered flip flop. That is, it will only work when it will be getting positive edge triggered. That is from 0 to 1. Then it is saying that if the preset or sorry, if the present state of the counter is q naught, q1, q2, that is this q naught is initially 0, then we have a q1 which is also 0, and then we have a q2 which is also 0. So it is saying then what will be the next state of the circuit. So this is quite basic. So first of all, these you can see are clearly t flip flops, and t flip flops we know the characteristic equation is qn plus 1 is nothing but t xor qn. That is, t if t is 1, then qn plus 1 is given by q and complement, and if t is 0, it will not toggle. That is, qn plus 1 will remain qn itself. So that is why it is also called as a toggle flip flop. So considering this equation, now we need to see, so see clearly here the clocks are not given at a single instant. So that is the basic difference between a synchronous, that is what we did in the last lecture, and a asynchronous counter. So there are two types of counters. Synchronous, what we have is we have n flip flops. Let's say n flip flops, and all of them are having a single clock. It can be negative or it can be positive as triggered. So these are the synchronous circuit in which we have a single clock. Wherever this asynchronous circuit can have different clocks. That is, the first clock is let's say it's driven by the second clock is driven by the first clock, and so on. And maybe it can be a combination of certain different combination, etc. So whenever a clock, there are dependence on the previous input, that is, circuits are known as asynchronous. And a single clock means synchronous counter. So just it was just a brief on what is the difference of this lecture versus the previous lecture. So you can clearly see here the clock is applied only when this signal has been given, or this signal has been given as an output. So it is now saying that initially, I am repeating again, so it is saying that initially all of them q naught, q1, q2 are 0. So let's write here. Yeah. So initially q naught, q1, q2 are 0, 0, 0. So now you can clearly see here t naught is 1. So I just here you can clearly see the relation. When t is 1, the next state will toggle. So whenever there is a t is 1 and we have a positive edge clock, let's say we have applied the first clock, then what we can see is this q naught or this qn plus 1 will become qn complement. So this q naught will become 1 and this q naught bar will become 0. Is there any doubt in this particular step that it is 1 and it is 0? So basically q naught has been changed to, I'm now writing here as 1. Now even only getting the input or the output of q naught, then only we can get the output of q1 now. So now you can clearly see here the clock is given as 0. That is, it has changed to 0. So this is a negative edge, not a positive edge. This clock will get triggered only and only if you get a 1 here. So this will clock will not work. So what does it mean? Even if t1 is 1, this next state will remain the same as the previous state. So it will still remain 0. So it will still remain 0. So q naught bar will be 1. So I'm still writing a 1 here. And now you can see a 1 is there. So yes, this positive triggered edge clock will work. But now the t naught, that is the t2 is 0. So now again the qn plus 1 will be q1 itself. So that is why it is still what it is before only. So initially what has happened? Give me a moment. So it was 0. Yeah. So q1 has become 0. So I guess I have not written it correctly. Yeah. So q1 has become 0. So after applications of all the clock, the state of 000 has changed from 100. So is there any doubt in particular uh, in this problem? Because it is quite conceptual. If you know the concept, it will be very easy, and if not, then I can repeat again if there is any problem. So you can tell me. Is it clear, everyone? Should I repeat? Okay, fine. Yeah. Okay, so first of all, I have already told about the synchronous and asynchronous counter, that if we have a single clock, then all the flip-flops work in a single instant. Whereas if we have different clocks, that is clock of a certain flip-flop is kind of dependent upon the previous flip-flop, then we are here having a asynchronous counters. So this is the case of asynchronous counter now. So I'm repeating again. Initially it was 0, 0, 0. So when we apply our positive edge or the first clock, what happens is this t naught was 1. So that is why the equation of the next state will be qn plus 1 will become qn complement. That is what t flip-flop offers, which is covered by the excitation table or the characteristic table of the flip-flop. So this 0 has now become 1. You can clearly see this has become 1 and q naught complement will be 0. Now you can clearly see this clock, which is a positive edge triggered clock. So the difference is this is a positive edge triggered flip-flop and this is a negative edge triggered flip-flop. Sorry. So it only works when the clock is 0, that is it is going from negative edge triggering, and it only works when it is positive edge triggered. So you can clearly see now the q naught complement has become 0 here. So once it becomes 0, this flip-flops will not function as it should be. That means whatever the previous state, it will still store the same, because here t naught is 1, but it will not be qn plus 1 will not be qn complement. It will be still remain the same because the clock has not worked still. So that is why this 0 has still become 0 here. So that is what I have written. So 1 it was, and the q1 has still remained the 0. And when it is 0, this q naught complement will become 1. So this is a positive edge now. So this t2 flip-flop will work as it should be, and t2 input was 0. So what it means is when qn plus 1 is equals to qn, because t is 0 now, it will not toggle. So the state that was initial was 0, so it will still remain 0. So from 000, it has given to 100, which is option C. Is it clear? Okay, fine. Is it clear to everyone? If you're having still having any doubts, you can ask.
Sir, can you tell me the next state?
Yeah, so the next state, sorry, after this or this, can you clarify your question? After 100 you are saying, or just this again?
The second state
Okay,
after
so
the it is the first state
yeah, so
when you
the
give a
question
first
is,
clock. The second clock, what happened? If the answer is 100,
yeah, sure, sure. So yeah, let's try that. So now the present state is now becomes 100. So let's try for one more clock. So let's say this is 1 now, this is 0, and this is 0. So when we apply the positive flip, what to say, positive edge again, so this T naught will work because of the T naught being 1, the next state will be Q1 complement. So 1 will become 0 here. So Q1 complement will become 1 here. Now this has a positive
0.
edge. So this will work. So since this is T1 was 1, so the previous state was 0. I guess, yeah. So this 0 will become 1 now. It will toggle. So this will become 0 and it will not work because the clock is negatively triggered. Sorry, the positively is triggered, and whatever the previous state that was, I guess, 0, yeah, 0 will become 0. So the next state will be 0 1 0.
Okay, sir.
Yeah, so I hope it is clear to everyone. So if it is clear, so you can try this question out now and let me know the answer maybe in 5 minutes what is that you are getting. This have got one answer. So let's wait for 1 or 2 minutes more to get more answer and then I'll solve it.
Sir, I think all zeros, but there is no answer here.
Okay, so you are getting all the zeros. So let me try it out then. So initially the state have now been given as 0 1 0. Sorry. Yeah. So now whenever I will apply a positive edge, so I am doing it here only quickly. Let's say this was the initial state. This was 0 1 0. So whenever I apply a positive edge trigger, this is 1. So qn plus 1 will be qn complement. So this will become 1, this will become 0. This clock will not work. So this will not work. Whatever the state, that is qn plus 1, will still remain the qn. So there will be a 1 here. This will be a 0. This will still not work. And yeah, this will not work. And again, the qn plus 1 will remain qn, because this is a negative positive edge triggered flip flop. So this 0 will still remain 0. So it has become 0. It has become 1 1 0, which is option C. Okay. So some of the students have already got the answer. So is it clear to everyone? Yes. So whosoever was saying all the zeros are coming. So is it clear now?
Yes, sir. Yes, sir.
Okay, fine. So let's move towards the next problem now. Maybe you can all try the same, and let me know the answer maybe in 2 3 minutes, and then I'll solve it. Okay, so just to clarify, this is, can anyone tell if this is a synchronous or a asynchronous counter?
Synchronous.
Yeah, so this is a synchronous counter since it has a single clock applied to each of the flip flop. So you, what you need to determine is the number of unused states. So I've already covered this concept in the previous lectures also. So you need to start with, let's say, 0 0 0 and go towards what is the counter offering, and then you need to check how many states are unused. So I'll give you maybe 5 minutes to solve this out, and then I'll solve out. So any answer? So if not, let me try the same. So we have, let's say, three flip-flops, so it is Q naught, so maybe I'm marking it as 0, 1, 2. So we can clearly see it is J naught, K naught is 1, then J1 is, okay, so this is 1, so this is Q naught, and this is coming out to be Q2 complement. So J naught is Q naught, Q2 complement, and K1 is directly, K1 is this, okay, so K1 is Q naught, then I have a J2 which is Q1,
Q1 into Q naught.
Q1 into Q naught, and then finally K2 which is again Q naught. So these are the relations that I need to be careful to solve this problem. So let me start with a 0, 0, 0. So let me consider this as in the same order. So J naught and K naught is 1, so it will toggle. So Q naught will become 1. Then Q1, okay, so J1 I need to calculate for the next step. So let me write here whatever J1 is I'm getting for each and every step. So here J1 will be Q1 Q naught complement, so that will be 0, and K1 will be Q naught, that will be also 0. So it will 0, 0 will hold the state, that is 0, and then Q2 is Q1 Q naught, that will J2 will be 0 again, K2 will be 0, so it will again hold the state. So from 0, 0, 0, this is the, let's say, first cycle, this is the second, and third I'm writing here maybe some different thing. So now again it will toggle for J naught K naught, because J naught K naught are always 1, as you can see. Then I'll calculate the J1 now. So it is Q1 Q2 complement, sorry, Q naught Q2 complement. So J1 will become 1, K1 will become Q naught, that is 1. So both are 0, so it will toggle, so it will become 0, 1, and Q2 is Q naught was 0, no, Q naught was 1, and J1 was, sorry, J2 was Q1 Q naught, so that will be 0, so it will still be 0. So are these steps clear? Still, I will solve it further, but are these steps clear till now?
Yes, sir.
Fine, then. So I'll now calculate J1, that was Q1, sorry, Q naught, Q2 bar, Q naught is 0, K naught is 0, so it will still remain the same, that was 1. Then I have a J2, that is Q1 Q naught, that is 0, and K2 will be Q naught, that is also 0, so it will still remain 1, 1, 0. Let me use some different thing again. So it will again toggle from 0, and then Q naught, Q2 complement J1 will become 1, K1 is Q1, so it will toggle. J2 is, what was J2? J2 was Q1 Q naught, so it will still be 1, K1 is 1, so it will again toggle, so 0, 0, 1. So it will now again toggle for the first state. Okay, let me use some different thing. Then J1 will be Q1, sorry, Q naught, Q2 complement, so it will be 0, and K1 will be 0, so it will remain the same. Then J2 is Q1 Q naught, so it is 0, and then K2 was Q naught, so it will still remain the same. Now it will again toggle. J1 is Q naught, Q2, so it is 0. K1 is Q naught, so this is 1, so it will be becoming 0. And J2 is Q1 Q naught, so it is 0. And K2 is again 1. So yeah, it will still. Okay, so we have reached the initial state again, I guess. So we have started from 0, 0, 1. So let me count the U state first of all. So we have three flip-flops. So the total number of states will be 2 raised to power 3, that is 8. So we need to, what we need to find? We need to find the number of unused states in this. So we have 0, 0, 1, then we have 1, 1, 0, 2, 3, 4, 5, 6. So we have got 6 used states, and then we have reached back to the original state. So this is what it will prefer. So used states are 6 in this question. So the finally the unused states will be 2. Is there any doubt in this particular question? Because it requires some of the knowledge of these flip-flops and how it works. Is there any doubt? Anyone? Anyone? Is there any doubt?
No, sir.
Okay, okay, fine. So let's proceed then. Maybe now you can try it. This is again a similar question. It just looks complex, but it is very easy. So you need to find figure below displays a mod n counter. So again, n is the use states. So you need to find out the use state, the value of n is. So again, be clear, this is a D flip flop now instead of JK. So this will be more easier to solve. So let me know what are the use states of these counters. Let me know all the states also and the unused states also. You can take 5 minutes to solve this and then let me know the answer. Okay, so can anyone tell what are the relations that they have got for D1, D2, D3?
Q3 bar Q1.
Give me a moment. Yes, so this is the relation for what?
D1
D1 is Q3.
bar Q1 plus Q2 Q3 bar.
So something like this.
No sir, no bracket.
Q3 bar are common in both these terms you are saying, na?
No sir, Q2 plus Q3 bar.
Okay. This is what you are getting.
No sir, there's no plus after Q2 plus Q3 bar.
There is no plus here.
Yes sir, now it's correct.
That is what I wrote, na? I took Q3 bar common.
Okay, okay sir.
Yeah, yeah. And then for D2,
Q3 bar into
hmm,
bracket Q1 plus Q2 bar.
Q1 plus Q2 bar. And for D3,
Q1 into Q2.
so let me quickly check. I hope everyone also is getting the same relation. Give me a moment. Yeah. So here I have a Q2. Here I have what is this thing? This thing is Q1. Okay, so D3 is for sure Q1, Q2. So this is correct. Then I have this is Q2 bar and this is Q3 bar. So this end is giving, okay, so this is giving as one thing here and this end also I'll check Q1 and this is Q3 bar. Okay, huh. Q1 plus Q2 bar. So yeah, this is, yeah. So D2 is also correct. I'm getting Q3 complement Q1 plus Q2 complement Q3 complement, which is giving me this. And then finally I have this. And so this is Q2, this is Q3 bar. It is coming here Q3 bar Q2 and this is, okay, so this is what I already have. This is Q1 and Q3 bar, which is getting OR. So yeah, Q3 bar will become. So yeah, D1, D2, D3 will be coming out to be these expressions only. So these are correct. So now using these, let me try to make what the number of states and number of mod counters. So let's start with again a 000. So we all know in D what we have is Q naught plus will be D naught, Q1 plus will be D1, and what else? Q2 plus will be D2 only. And we all have the expression. So let me try to go against it. So Q1, sorry, it is Q1, Q2, Q3. My bad. This is Q1, Q2, and Q3. Similarly, it will change here, so I'm not changing it. So this will be D1. So D1 is this big thing. So Q1 plus Q2 is 0, and then 1 times 0 is 0. So this is the first step that I'm writing. I'm just evaluating these expressions. So this will be similar to, let me write again, D1, D2, D3. So this is 0. D2 is D2 is this thing. Q1 plus something. So 1 times 1 is 1. And then Q1, Q2 is 0. Is it clear this step? Everyone, is it clear? Please respond if this is clear so that I can proceed ahead.
Yes sir.
Okay. So now, I have again 0 1 0. So D1 will be, first of all, D3 is very easy to calculate. So it is 0. D1 will be Q3 complement, that is 1 times something plus something. So this will be 1. D2 will be Q3 complement times Q1 plus, okay, so it will become 0. Again, I'll write D3 is Q1 Q2, so it is 0 again. D1 is D1 is Q3 complement is 1. So Q3 complement is 1 times 1 is 1. And then Q3 complement is again 1. 1 times Q2 complement, yeah. This will become 110 now. So this into this will become 1 now, Q1, Q2. Q3 complement is 1 and any of them is 1. So I guess all of them will become 1. If I have done some mistake, please stop me there only because I'm also not sure. So again, this will be 1. And what else? So Q3 is 0. So okay, so these will become 0 for sure. And again, this will be 0. And then Q3 is okay. So these two will be 0 again. Okay, so I've got the initial state again. So let me count the number of states now. 1, 2, 3, 4, 5, and 6. So this is nothing but a mod 6 counter. So mod n counter, the value of n is 6. Here the unused states are 2. So answer to this question is 6. Is it clear to everyone?
Yes, sir.
Fine, and so we can proceed, I guess. This is again a similar question. Maybe you can try it out. This question has some twist because it has a propagation delay. So maybe you can try it out and let me know whatever you are getting, and then I'll solve it. Or let me try it out because it has a reset pulse and I have not covered the concept. So in this question, it is given. So what is this? Mod 8. So I've already got one answer as mod 8. So let's see if it is correct or not. So in this question, it is saying that consider the circuit shown below. Let the propagation delay of the NAND gate. So propagation delay of NAND is 2 nanoseconds, and that of the counter is 0. So counter has not any propagation delay. If the applied clock pulse is 1 gigahertz frequency, then the modulus. So mod is fine. We need to again find the mod of the counter. So 1 gigahertz means the time period is 1 by 1 giga, that is 1 nanosecond. So every clock is getting positive edge triggered in 1 nanoseconds. So now this is nothing but a 3-bit synchronous counter. So that means it is a, let's say, consider it as a up counter only. So it is going from 001 to 001 to 010 and so on. So we'll consider each and every state because of this reset pulse. So what is this reset pulse does? If this becomes, since this is a reset complement, or if there is a bubble here, so if reset input is 0, then the counter will get set to 0. So any state it was before, it will change to 000 if this reset bar becomes 0. Is it understood, this particular thing that I have just said? Is there any doubt?
Can you repeat, sir?
Sorry.
Can you repeat, sir?
Okay, okay, I'll repeat. So what I have said is there is a reset pulse here. You can clearly see there is a reset here. So whenever this becomes 0, what happens is when reset is 0, the counter stops counting and it gets set itself. The output of this counter, that is Q0, Q1, Q2, will always become 000. There will be no further counting if this is 0. Otherwise, if this remains once, there will be a similar counting as the clock as we generally do. That is this. So it will go from 010 to 011, then 100, similarly like that. So there will be total 8 states because of this 3-bit counter. But whenever this reset will become 0, that is reset complement will become 1, or this bar and bar will get cancelled. So whenever this will get 0, what will happen is it will stop counting. Is this thing clear to everyone?
Yes, sir.
Okay, so now we'll check for each and every state. So we have started from 000. So this is the LSB 000. So now this is, look carefully, this is a NAND gate with two bubbles in the input. So one is here and one is here. So what I'll do is I have put 000 here. So it will become 101 here. Do you understand this? How I've written 101?
Yes, sir.
So the output of this will be 1 of the NAND gate. So since this is 1, so it will not reset. So it will go to the next state. So 001 will be the next state. So now I'll check for 001. So 001, it is 001 now. So this will become 100. Again it will become 1. So it will go from 001 to 010. I hope these steps are clear. So now what is it is? It is now 010 or 010. So sorry, this is 0. So what happens now? This has become 111. Okay, so now it has become 111. So the output of this will be 0. So what will happen now? This will stop immediately at this state only, and the next state will become 000. So it will only count 3 states. So that will make it ideally a mod 3 counter. Is there any doubt till now?
No, sir.
So if not, so the twist in this question is now this particular NAND gate has a propagation delay of 2 nanoseconds, whereas the clock frequency is 1 nanoseconds. So what will happen is there will be two extra states that will get counted because of this frequency or this time period. Because this NAND gate will take 2 nanoseconds to deliver the final output. So there will be two more states that will get counted, that is maybe 011 and 100, and then it will go to 000. So these two are because of that 1 nanosecond and 1 nanosecond propagation delay. Is it understood? It is quite complex, but it is very easy if you understand the problem. Is there any doubt in this, what I have just said?
Sir, can
Sorry?
nanoseconds time, we are getting delay of 2 extra 2. If
Yes,
there is a 2 nanoseconds means we are getting one time delay.
yeah, okay, so I'll clear it out again. So here we had a pulse. So whenever the first nanosecond starts, because of the 2 nanosecond delay, the first pulse will be giving you the output, and then the second nanosecond when it will start, the second pulse will be giving you the output. The counter has not any delay. It is clearly mentioned that the counter delay is approximately 0. So every clock pulse, every 1 nanosecond, you are getting a state. So that is why 2 nanosecond will be giving you 2 state instead of 1. Is it clear?
Oh, okay, sir.
Yeah. So there will be total mod 3 plus 2 states. That is, this is a mod 5 counter, which is option C. So this is a working of reset pulse basically. This is a concept, maybe it is covered in the theoretical lectures also. Whenever it gets 0, the counter stops counting there only. Is it clear to everyone? Is it clear everyone?
Yes, sir.
Okay, so let's proceed then. So now again, this is a very basic question. Maybe you can try it out and let me know the answer in 2 minutes. So I've got one answer, I guess. What is that? 7 is one of the answers. So let me try to solve it. How many flip-flops are required to make a mod 129 counter? So 129 basically, okay, so we'll check all the options. So we already know that, let's say if we have m flip-flops, so this should be greater than n, where m is the flip-flops and n is the mod. So why? Because for two flip-flops, what we have is we have four states. Similarly, for three flip-flops, we have eight states, and so on. So here it is given 129 counter. So 2 to the power raised power m should be greater than 129. So I'll check for m equals to 6. I'm getting 64, which is not greater than 129. For 7, I'm getting 128. 128 is not greater than equals to 129. But for m equals to 8, it is 256. So this is the first stage which is getting satisfied by this particular equation. So we'll require a minimum of 8 flip-flops to make this counter. So 8 will be the answer, not 7. Is it clear, everyone? This was very easy, I guess.
Yes,
Fine.
sir.
So yeah, so quickly let me know the answer to this. This is again a similar problem.
How many minimum number of flip-flops required to make 479? It is a 9, sir.
Okay, so again, 2 raised power m should be greater than or equals to n. So we have already done the calculation till 8, I guess. So 2 raised power 8 was 256, which is not greater than 479, and 9 is 512, which is greater than 479. So yeah, 9 is the answer. So let's proceed ahead. Again, this is a similar problem as we have done previously. So maybe you can try it out in 2 minutes and then I'll solve it.
As in the following figure, suppose you are asked to make the
So what my answer is OR gate. Okay, so we'll check. Any other answer? Maybe in 1 or 2 minutes. So I've got XOR now. So let's check. I've got few answers which are different. So stage 2, 3, 4, 5 needs to be 1. So let me simplify it. Okay, so there are ABC counters. So I'll consider this as MSB. Let's say this is LSB. So when it is 1 is we need to make a decoding circuit when the counter is at state 2, 3, 4, 5. So let me write all the possible states, that is and it needs to be 1 when it is 2, 3, 4, 5. So in decimal maybe I can write it is 0, 1, 2, 3, 4, 5, 6, 7. So it is 2, 3, 4, 5, I guess. So it needs to be 1 here, else it can be 0. So maybe you can make a K map quickly, and this is very easy to solve. It's 2, 3, 4, 5. So I'll write again 0, 1, 2, 3, 4, 5, 6, 7. 2, 3 is here and 4, 5 is here. There will be two pairs. So what I have written is C complement C. Sorry, this will be C. A bar B bar A bar B. This will be AB. This will be A bar. The answer will be here. C will be common. A bar C plus C bar A, which is A XOR C. Yeah, so A XOR C. So Y needs to be 1. So we need to apply this gate as A XOR C. So we have a direct A, we have a direct C. So B needs to be disconnected, and this can be changed by a logic gate of XOR. Yeah, so XOR will be the correct answer. That is option C. I hope. Yes. So is it clear to everyone? Any doubts here? So quickly
So
let me
the
know the
MSB should be
answer.
right side.
Yeah. Hello. Yes.
MSB should be right side. Sir.
Sorry.
How are you taking MSB on right side and LSB on left side? Sir?
Yeah. Okay. So I have just assumed it. If you will assume the reverse also, let's say this is ABC. Let's say this is ABC. So then you will get the answer maybe as this will become A, this will become BC. So you will get maybe BX or C or something like that. That is just I assume. That
Okay,
is
sir.
not a problem. Yeah. You can assume this as MSB also if you want. So quickly let me know the answer if this is the operation. Instead of 2, 3, 4, 5, I want 1, 2, 3, 5, 6, 7. Options are same. Quickly let me know the answer in 2 minutes.
or gate, sir.
Okay, yeah, so yes, this will come out to be OR gate because this is the truth table for OR gate only. So I have written quickly. So I hope it is clear to everyone. So let me also show. So I have written 1, 2, 3, 5, 1, 2, 3, 5, and then 6, 7. So if I do it in this schema, it is 1, 2, 3, 1, 2, 3, 5, 6, 7. So this will become 2 quads, and this will be nothing but B plus A, or A plus B, whatever it is, according to your MSB LSB. So this will be a OR gate. So let's proceed now to the further problem. So yeah, this is a good problem. Maybe you can try this out. We can zoom it. So you need to find the mod of this counter, mod value. Again, so I'm writing this is A0, A1, A2, this let's say A3. This is count enable. You can assume it to be C, which is the clock basic, not clock, but the input to the J and K flip flop. So basically, if C is 1, this will imply J and K will be 1, and it will the input will toggle. So you can again start with 0, 0. These are 4 flip flops. So 0, 0, 0, 0, and go till whatever the countings that you are having. Maybe you can take 2, 3 minutes and let me know if you are getting any answer, and then I'll solve. So let me try to solve it out. So this is count enable. This needs to be 1. So let me first of all try to write the equations for J and K. So J0 and K0 will be 1. Then J1. So this is 0, 1. I am assuming like that. J1 will be equals to K1, and that will be AND of A0 and C1. Sorry, C. Then J2 and K2 will be AND of A1, A0, and then C. And finally J3, K3 will be AND of A3. Okay, wait. A2, A1. Sorry, A3 is nothing, but A2 is there. Then this is A1. So this is J2. A1, yeah. So J3 is A2, A1, A0, and then C. And yeah, so next state is nothing but yeah. So we need to be bothered about these only. So is it clear first of all? These all the relations that I've got. Any doubts here? Fine then. So we'll again start. So these are the. So we'll again start with this. Let's say A naught, A1, A2, A3. So I'm writing it here. So we'll start with 0, 0, 0, 0. Or we can, what we can do is we can have like that. That will be easier to solve. First of all, this count enable will always be 1. That means this will always toggle. Whatever the state will be, this will always toggle in each and every further state. So I'm just writing it directly, the A naught part. So now what I'll try is to calculate A1. So A1 will be calculated by J1 K1 here. So previously it was 1, so J1 will be, so I am writing each and every state, whatever J and K I'm having. So it will be 0, J1 is, K1 is 0, so it will remain the same. So rest of them will be 0 because of the AND relation. And then here I have A naught and then C, so this will become 1. And then J2 will be, these two will be 0. Is it understandable to everyone? These two, the calculation that I have done. Should I explain them more? Please let me know if this is the case. Is it clear? Please respond. Okay, fine. So again, this J1 will be A naught into C. So A naught is 0, so this will be 0. Sorry. Yes, I guess I've written it. No, no, no. This is A1. A1 is J1 K1. So J1 is A naught C. This will be 0, 0, 0, 0, 0, 1, 0, 0, 1, 0. Then this will be 0 again. This will be A2. This will be 0 again. What is A1? A1 is making, okay, so yeah, so it will remain the same. J and K will be 0, so it will hold the state J1 and K1. And then what it is, then J1 and K1 will become 1, so it will toggle. J2 and K2 will be A1, so will still be 1. So it will again toggle, so this will remain 0. Please stop me if I'm making any mistake anywhere and I'm trying to solve it. So you can also try to solve it on your own also. So this is 0, 0, so this will again remain the same. So again 0, 0, and this will be 1. Now A1 is 1, so this will toggle now. This is 0, so this will not toggle. Now this is 0, so this will not toggle. This is again 1, 0. This will again not toggle. This will be 0. I hope I'm doing it correctly. 1, this will toggle, 1, this will toggle, 1, this will toggle. 0, no, no, no. Then 1, this will toggle. No, no. 0, this will remain the same. 1, 0, 1, 1. Then I have 1, so this will be, this will be 0, sorry. This will toggle, this will remain the same. I'll write more of these. I need to go it till I'm getting a 0 back again. So, this will remain the same. This will remain the same. Again, this will toggle. This will remain the same. This will remain the same. And finally, 0, so it will remain the same. Okay, so I guess this is this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So I'm getting all the states here. Is it right? Are you also getting the same? Please confirm if I've done it correctly. If yes, then this will be a mod 16 counter. Yeah. Hello. Hello.
Sir, could you repeat how the table is coming?
Yeah, I'll repeat again. Fine. So I have got these relations. So I need to now work on it. So basically, this is one. This will be a naught. This will be a1 a naught. This will be a2 a1 a naught. So I'll try to explain two three in between the tables, two three steps. So let's say maybe this is the step that is 3. So a naught will always toggle because j naught and k naught is 1. So I have directly written 0 1 0 1 in this order. For a1, what we need to have, we need to find the j1 and k1. So j1 and k1 will be here I am writing. So j1 and k1 will be a naught only, which is 0. So it will hold the state whatever it was. Sorry, a naught was 1 in the previous state. So sorry, it will be 1. So it will toggle. So this 0 will become 1. Similarly, for this j2, I need to find out a1 a naught. So a1 was 0. So j2 and k2 will remain 0 only. So it will hold the state. So this 0 will become 0. And similarly, a3 will be always also 0. So these two are getting hold and this one is getting toggled. So that is how I got the next state. Is it clear? This particular step. Hello, is it clear? If not, please let me know. I'll explain again.
No, it is not clear.
Okay, fine. So maybe I'll try to show you some other step that will make it easier. Yeah, sure, sure. So let's say this is the state now, which is state 8, it is saying. So what has happened is in the previous state, A naught was 0, A1 was 1, A2 was also 1, and A3 was 0. So I will calculate the J naught and K naught, or this is always toggle. So I'll calculate the J1 and K1 from the previous state, and J1 and K1 is nothing but A naught. So J1 and K1 is A naught, so it is 0. So this will remain the same because it will hold. Similarly, now J2 and K2 will be what it will be. Uh, J2 and K2 will be A1 times A naught, so that will be again 0 because A1 times A naught will be 0 because of the AND operation, so this will again hold. Similarly, J3 will be again A1, A2, A3, so this will again be 0 and it will again hold. Is this step clear? Okay, fine. So these are this is what I have done in the whole table, and this is what I have got for all the 16 states. You can also try it in your homes also to solve this again. So this is nothing but a mod 16 counter.
Okay, sir.
So yeah, so if this is clear, okay. So let's proceed to the next question now. It says the clock frequency of 15 uh, megahertz is applied to a cascaded counter of mod 3, then it is cascaded to mod, sorry, mod 3 is cascaded to mod 4, which is cascaded to mod 5. And the frequency is 15 megahertz. So first of all, the cascading mod counters are nothing but overall mod is the multiplications of all the mods. So this will be 3 times 4 times 5, that will be 60. And what is the lowest output frequency? So it is getting calculated by 1 by n tau pd, or 1 by n of time period. So let me give it. So the frequency, sorry, f low, let's say I'm denoting it, it is calculated by the actual frequency or the overall frequency by the overall modulus. This is a basic what to say formula question. This might have already been taught in the class also. So the actual frequency is 15 megahertz, by 60 will be the overall lowest frequency, which will be, I guess, 150 1500 into 123 kilohertz. This will be by 60, so 60 60, so 250, so this will be 250 kilohertz. You can also check the calculation. So the final answer will be option B. Is it clear? Please let me know quickly.
Yes, sir.
So yeah, let me know the answer to this. This is again a similar question. Okay, so yeah, I got same answer. So yeah, this is very easy. So the overall mod is, I guess it is 4 times 5 times 6. So this is 120, and the frequency will be overall is 12 megahertz divided by 120. So it is 12 3 kilo by 120. So this will be 100 kilohertz. 100 and 120. Yeah, option D is the correct answer. So again, this is a similar type of question. It is saying 3 cascaded decade counters. Decade counters means mod 10. Will divide the input frequency by. So it is 3 cascaded mod 10 counters. So the overall mod will be 10 times 10 times 10. So it will be 1000. So option C is D is the correct answer. So I'm doing it quickly because this is very easy. Yeah, so maybe you can try this question out. This is saying now to consider the following sequential circuit with X input and positive X trigger D flip flop to determine the self loop state from the state transition diagram. So I hope state transition diagram has already been covered in the lecture. So maybe you can try it for 5 minutes and then I'll solve it. Okay, so I still not got any answer. So let me try to solve it out. Um, it says now, consider the following sequential circuit with X as an input and Y as an output with a positive edge trigger D flip flop, and it is having a single clock. So again, this will be a synchronous circuit. So we need to find the self loop states from the state transition diagram. So basically, we need to make the state transition diagram. So D naught is clearly X, it is given. D1 is Q naught, it is given. So we already know that Q1 plus is D1, that is nothing but Q naught, and Q naught plus is D naught, which is basically X. And here Q1, Y is nothing but Q1. Is there any doubt in this? These are the basic equations that are already,
Yes.
yeah. So if this is clear, so we just need to make the state diagram. So in state diagram, what we need to have is, we need to have the inputs. We can check the input of flip flop. We can have next state, and finally what we can have is the final output. So this is what I meant. So I will write all the things. So the inputs can be Q1, Q naught, and X. D1, then we have the next state that can be calculated by D1, which is Q naught, I have just shown you, and D naught, which is X. Then the next state will be uh, Q1 plus, and this will be the next state, that will be Q naught and X again. Okay, so let me write Q1 plus, which is Q naught, and Q naught plus, which is X. And the final output is Y, and Y is nothing but Q1 again. So I'll write the table. So I'll write all the combination. So our D1 is Q naught, so I'll repeat the Q naught bit again. D naught is X, so I'll repeat the X again. Q1 plus is Q naught, so again I'll write the Q naught. And Q1 plus is X, so again I'll write the 0 ones. And Y is finally is Q1, so Q1 is this 0 0 0 0. Is there any doubt in this table? Please let me know if there is any. Y is Q naught or Q1?
Sir, sir,
Yes.
this portion is I am not getting first portion.
This is
D
Q0.
naught is equal to X, D1 is equal to.
Yeah, okay, fine, fine. Yeah, you can. What you are saying? Yeah, please repeat.
The first D naught is equal to X. It is okay, sir. Uh,
Yes.
D1 is equal to Q naught, okay, sir.
Then the next
Q1
state,
plus
yeah. So next state of D1 is
is
nothing
equal
but,
to Q1.
yeah, D1
Okay.
is Q naught. Then again the next state of D naught is again it is given X, and Y is the next state. So Y is Q1 plus. So this is what I have written wrong. So this will be Q naught. So I'll just have to change this thing. Q naught is what? 0 0 1 1. Is it fine? Any doubts here? So if not, then let's make the state transition diagram. There are four possible states. We already know this is 0 0 0 1 1 0 and 1 1. So you can see in the first state, maybe I can make with some different ink. 0 0 is getting changed to 0 0 when input is 0 and output is 0. 0 0 is getting changed to 0 0 when input is 0 and output is 0. Again 0 0 is getting changed to 0 1 when it is 1 and this is 0. Now 0 1 is getting changed to 1 0 for 0 1, I hope it is clear. This is very easy. So 0 1 is getting changed to 1 1 when it is 1 1, and 1 0 is getting changed to 0 0 when it is 0 0. So 1 0 is getting changed to 0 0 1 when it is 1 0. 1 0 is getting changed to 0 1 when it is, sorry, when it is 1 0. Then finally what we have is 1 1 is getting changed to 1 0, and this is getting changed to 1 0 when it is 0 1, and finally 1 1 is getting changed to 1 1 again when it is 1 1. Is it clear, the state diagram, all of you? Any doubts in this?
No, sir.
So yeah, so you can clearly see there are only two self loops, which are 0 0 is getting changed to 0 0 and 1 1 is getting changed to 1 1, when they are 0 0 and 1 1 respectively. So the answer to this question will be, yeah, option C. Is it clear, everyone? Yeah, I hope it is clear, so we can move forward. Okay, so it is again a simple question which is already done. So a certain JK flip-flop has a propagation delay of 40 nanoseconds. The largest modulus of a ripple counter that can be constructed is, it is asking for a frequency of 8 megahertz. So frequency is nothing but 1 by n tau PD, and n is nothing but this. Both of these things are given, so you can calculate 1 by 40 nano into 8 mega. So this will be 10 raised to minus 3 thousand. So this will be 100. 100 by 32 is 3 point something. 3.1 to 25 to 3.125. So yeah. So largest it can made is, what it is, a certain JK flip flop. So these are the mod n. So 2 raised power 3.125. 2 raised power 3 is 8. So D will be the correct answer. Is it fine? Any doubts? This was a direct question, so I have not taken much time. Is it fine, everyone? Fine. Okay. So maybe you can take this problem as a homework problem because it will take some time. So you can take a screenshot here and let me know the answer in the next class. This is again an exact same problem which we have already done for that mod 16 counter. You want to do it here only? We can do it if you want, but this is very easy. Quickly let me know if homework is fine. Hello, is it fine? Please let me know. am I audible, everyone? Please let me know if you are taking this as homework or solving it here only. So I'm still not getting any response. So in this question, MSB is C and LSB is A. It is given.
Sir, we will do it, sir.
So fine. I hope you have already taken the screenshot and let me know the answer in the next class.
Okay, sir.
Yeah. So you can do these questions. This will not take much time. So now try to solve this in 2 minutes and let me know the answer. So again, this is very simple. So I'll calculate if you're not getting the answer. So Q1 plus will be
D.
D1. It will be, sorry, any answer that you have got?
Option D.
Okay, so we'll check if this is option D. So Q naught plus will be D naught, which is D naught is this thing, which is Q naught XOR. So sorry, not XOR, it is NOR. So Q1 complement. So yeah, so I'll quickly write. So Q1 Q naught. So let's say it is started from 0 0. So what will happen is Q1 plus will be Q naught. So sorry. So I'll write the LSB this side to make it easier. So what is now? So Q1 plus is Q naught. This will become here, and Q naught plus will be the whole bar. And so this will be 1. This will come here. This will be 0. This will come here. This will be 0. Yeah. So from 0 0, it is going to 0 1. It is going to 1 0, and then again going to 0 0. There are 3 states only. So the options are 0 0 0 1. 0 0 0 1 0 0 0 1. Okay, all the options are. So 1 0 is the third state. 0 0 0 1 1 0, and then again 0 0. Yeah, so option B is the correct answer. So you are getting A. I hope it clears your doubt. One,
Yes, sir.
yeah, fine. Quickly let me know the answer to this now. This is again a similar question. You need to count all the states because it is a divide by counter. So you need to find the mod of this particular. So got one answer is mod 5. So let me quickly try to do it. So this is 2, this is 1, this is 0. So q naught plus is d naught, which is again q2, this is q1. q1 plus is d1, which is q naught. q2 plus is, what is q2 plus? Is d2, which is q1. q2, q1, q naught. So let's start from 0, 0, 0 again. So q1 plus is, so q2 plus is, so this is, this 0, 0 will come here and this will be 1. The 0, 1 will come here and this will be 1 again. This 1, 1 will come here and this will be done something 0. Then 1, 0 will come here. This will be 0. Then 0, 0 will come here. This will be, I've done something wrong. Let me check 0, 0, 0 again. 0, 0. And then this is q2, q1. So this is it the same? I'm not sure. So this is 1, 2, 3, 4, 5 are the states. What are the answers that you have got? Yeah, 5. Yes. So mod 5 counter. So it is option 1. Is it fine, everyone?
Yes, sir.
So again, we need to find the clock frequency for a 4-stage ripple counter utilizing flip-flops, with each flip-flop having a propagation delay of 20 nanoseconds. So you can again do this by this. Sorry. You can do it at home also. This is very quick. So this will come out to be 12.5 megahertz. And yeah, so this is the question. So there was a question in which we did using D flip flop, in which we got the relation for, I guess, D2 was something Q3 complement Q1 plus Q2, Q3 complement, and there was some D1, we have the relation such as, I guess, I'm not sure, and D0 was something Q1 Q2. So this is again a similar question which is given in some different what to say, different representation to do it using the T flip flop. So this is the exact same question and you will get the same answer also. So you can take a screenshot of it and then maybe try it at home. You will get the same answer as you have got previously also. This is a simpler representation to that particular question. That is what I'm saying. So yes, is there any problem in today's lecture? Any particular problem that you are having? Because then we'll quickly wrap up the session now. Is there any issues? Anyone? So if not, then we can wrap up the session. Thank you everyone for attending the session, and we'll meet at the same time in the next week. So yeah, that is it from my side. Thank you everyone for attending the session.